Good afternoon to all the budding young chemists who are listening to this lecture. Let me start by paying my condolence to the thousands who have fallen prey to the virus COVID-19, and also mourning the loss of Dr. Stewart Warren, who passed away on the 22nd of March, an outstanding figure in the field of organic chemistry. And besides this, an excellent teacher who made things so much simple and interesting for all his students. At the same time, I pray to the Lord to lead us from darkness to light in this gloomy situation faced by the whole world today. Tamso ma jyotirgamaya. May He give strength to those striving relentlessly to bring hope to all of us. Un sabhi ko shat shat naman. The topic today is the importance of order of events in synthetic chemistry. Order is the need of the hour, and nature has always followed it. So be with the reactions. The synthesis is being planned on paper, using a pen, like the planning of a house. That is, a blueprint is first prepared so that time, reagents, effort, and money is not wasted. In other words, a systematic approach to be later used practically in the lab. Now, the first guideline, I hope you can all see. Now this is, well, I've improvised using one of my veranda walls. Guideline 1, this is the retrosynthesis. In other words, the reverse of synthesis. The target molecule 1, I've named it as 1. It can be disconnected using two pathways. Pathway 1, that is A, or B. If we disconnect it by A, so what do we get? These two synthetic equivalents. Now, can we go the reverse of this? That is, start our synthesis using these two synthetic equivalents. What happens when we try to synthesize our target molecule? As can be seen, this is the wrong orientation. Why the wrong orientation? Because carbonyl group, we all know, it is meta-directing, not ortho-para, meta-directing. So what will happen? What will we get? Here, we have the alkyl group in which position? It is present in the para position. So, if we start using the synthesis with these two synthetic equivalents, these two as the reagents, then we will get the wrong orientation. In other words, we won't be able to get the desired compound, that is our target molecule. Now coming to pathway B, if we use pathway B, in that case what will happen? Using pathway B, we will get these two synthetic equivalents. And as can be seen, this is the right orientation. Why? Because we know this alkyl benzene, it is ortho-para directing. So we will get our target molecule, that is the desired molecule. Let's see, write the synthesis. Here we write the synthesis. This is the synthesis starting with benzene. Friedel-Crafts alkylation. We get this alkyl benzene. Then Friedel-Crafts acylation, and we get our target molecule, that is molecule 1. So the correct orientation, that is the first thing to keep in mind. Now the guideline 2. This compound, again, like the previous one, target molecule 1, which is the target molecule 1, which we had covered earlier, that is used also in the fragrance chemistry, similar to this. That is a fragrance compound, and target molecule 2. This is also a fragrance compound used in the perfumery industry. This is musk odor it has. So it is used for retaining and holding on to the fragrance for a longer time. It is added. Now how do we go about the disconnection? Well, the first and foremost, as we can see, will be the RX disconnection. Why the RX disconnection? Because carbon, nitrogen to be disconnected. R carbon, X the heteroatom nitrogen. Why? Because we know that the nitro group is meta-directing and ring deactivating, being electronegative. So what will we do? We'll disconnect it first. No negativity, no negativity desired. So electronegative, any electronegative group of the nature like NO2, which retards the rate of reaction and of course will also give us the wrong orientation with respect to 1 or 2. It is disconnected first. A green approach. Anything which deactivates the reaction is removed first. Here. So we will get after removal. This will be the synthetic equivalent. Now this can be further simplified. How? By removing either of the two alkyl groups. Now the question arises, which one should be first removed? The tertiary butyl or the methyl? As we can see, it will be more favorable, in fact, if we remove the tertiary butyl. Why? Because we can add either of the two while going in the reverse step, that is the synthesis, by Friedel-Crafts alkylation, but the methyl group is present at a meta position with respect to the methoxy group. And we know the methoxy group is strongly ortho-para directing. It won't direct the methyl group to the meta position. So, and the tertiary butyl group, of course, is present ortho to the methoxy. So we remove the tertiary butyl group rather than the methyl group. And here we will get our synthetic equivalent, that is this ether, the phenyl ether, phenyl methyl toluene meta. Okay. And at the same time, the tertiary butyl chloride. These are the two synthetic equivalents. Let's try and reconstruct, that is synthesize. Can we do it? So starting with this, how do we go about it? This is very commonly available. The raw material should be easily available, okay? As we have stressed even earlier in our lectures, in the classroom lectures. So here we started how? By methylating this phenol. So this we get the ether. Now after this, the common reaction, that is Friedel-Crafts alkylation. This is what we get. And this on nitration, see, on nitration what will happen? The O-methyl group is strongly ortho-para directing. So one NO2 group will be directed at the ortho and the other at the para position. And here we will get our target molecule, because this was the structure of our target molecule. NO2 group, one at the ortho and the other at the para position to this methoxy group. So we prepared this flavor compound, and hey, yes, great chemists at work, okay? So you'll be so happy. You'll see when this is put to practical use that yes, this reaction is practically feasible. We know the chemistry behind it. Now guideline 3, this compound with two phenyl rings, a COH and a Cl ortho to each other. This has been studied for its liquid crystal behavior. Very important liquid crystals, as you all know. Now, how do we go about it? See, the COH group is not, we can't just introduce the COH group like that in the ring. So here we use another very familiar feature, that is we are going to use, you'll see, nucleophilic substitution in this case. How? First, we go about the functional group interconversion, so that COH is converted to some other familiar group which can easily be converted back into COH while we are trying to synthesize this, while going reverse. See, whenever we are moving forward, this double-lined arrow, that is retrosynthesis, disconnecting it, then at the same time it should be kept in mind that will the same reaction or the same product will we be able to get? We just can't, we can't break it at any portion we feel like. we have to keep the chemistry in mind and the reactions in mind and a logical approach in mind. So keeping this in view, we can see here by functional group interconversion, we place it the CN group, cyno. Why? We know on hydrolysis, yes, the CN group will lead to the COH group. And how can the CN group, how can this be introduced in this ring? We know by nucleophilic substitution. So what do we do now? Now the next step, what do we do? Which is the group which is easily converted into CN? Now let's recollect some of our chemistry that we have done earlier in our BSc classes. That is, if we replace this by NH2, amino group. Now see, instead of CN, we are writing amino. How? Think about it. Do you know of means where the NH2 group can be converted into CN? Yes, very well. We know that on diazotization, if we diazotize this group, NH2 group, that is using HCl NaNO2 0 degrees centigrade, and then treat it using copper catalyst and copper cyanide, what happens? Do you remember? The familiar Sandmeyer reaction. Yes, so that's the way we'll interconvert when we go back the NH2 into the CN, okay? So see, it's not that CN, why are we writing NH2? NH2 can easily be changed into the CN group by means of nucleophilic substitution. Now, we simplify this molecule further. That is Rx again. Cl and C. By mistake, I think I've written 2Cl, but it should be CCl. That is disconnected. And here, we get this compound. See, the two phenyl rings and the NH2 group, diphenyl, okay? So what do? We can further simplify it. How? We know the NO2 group can easily be interconverted into the NH2 group, because NH2 again will require nucleophilic. So any other group which can be converted into NH2? You know, benzene ring strongly, it has so many electrons. So basically it attracts what? Electrophiles. NH2 will be a nucleophile. So any reaction which can easily occur will be electrophilic rather than nucleophilic. Of course, that was a different thing altogether, where we diazotized it and conducted the Sandmeyer reaction. But here, see, NH2, recollect any group can be converted into NH2? Yes. NO2 on reduction. And nitration is a process we are familiar with. Nitro group is a very good electrophile. So, again, functional group interconversion. And here, we convert it into the nitro group. And once again, carbon heteroatom, CN disconnection, and we get this very, very simple molecule to start with, the diphenyl or the biphenyl. Let's see how the synthesis now will occur. That is, going back. Is it logical? Have we taken the correct step? We can see it one by one. And the last step becomes the first, and the first step becomes the last, as you know. So here, we nitrate this. On nitration, we will be getting this nitrated biphenyl, which on reduction will give us the amino group, which we are protecting by acetylating it. So NHAC, acetylation protection. And now this on treatment, on chlorination, amino group is again ortho-para directing. Para position is blocked. So we will get this ortho-chloro-derivative. Okay. This ortho-chloro-derivative, now what is to be done? Now comes the most commonly used reaction, nucleophilic substitution. That is this, what you can recollect is the Sandmeyer reaction. So NaNO2 HCl and using copper 1 cyanide, we get CN, nucleophilic substitution. CN, a nucleophile. A good method of introducing the CN, the nucleophilic group, which otherwise would not have been introduced under any other circumstances. So it's a simple reaction. Now this on hydrolysis will give us the target molecule 3. Here. So we get this target molecule 3. We are happy chemists, okay? Chemists at work, very happy that yes, finally we have achieved what we were trying to. Now let's move on to this next disconnection. This is, I had less space on this, so it's a little crammed. I hope you're able to follow guideline 4. Now this target molecule which has been depicted is basically used in producing anesthetics. You know, anesthetics are so important, while anesthesia, very important for surgery, rather scary, okay? So now see, this is used for producing anesthetics. And if you can see in this one very strange thing, and this why this guideline therefore said, because see in this case, two very prominent groups which are ortho-para-directing, the OR and the NH2, they are placed meta to each other. So how do we go about placing two groups which are basically ortho-para-directing meta to each other? Once again, the known principle of functional group interconversion first, and then of course we'll be placing a dummy group. Let's see this dummy. Dummy means it's just placed there for certain orientation, then we'll remove it, you know, it has no further use in the compound. So it will be just used as a dummy group. How? Very interesting, rather interesting, I think. So let's see. By functional group interconversion, because we know NH2 can't be introduced directly, it's a nucleophile. So functional group interconversion, the other group NO2, which can easily be converted into NH2 here. So NO2. Now, what happens? Now comes the part of the dummy group, you know. So we add the amino group here. The amino group is added how? In such a way so that, because amino is ortho-para-directing, so it is placed in such a position that when we are doing the reverse, the NO2 will be guided to the ortho position of NH2 so that it automatically becomes a meta-placed group as far as OH is concerned. And NO2 we know can easily be converted by reduction to the NH2. And later on then we'll remove this NH2 because that is a dummy group. We don't require it in the molecule. So this is placed. NH2 is placed in such a position so that it guides NO2 when we are going back in the reaction. That is rather, we are trying to synthesize it because this is the reverse. So NH2 is placed here. The dummy group. What does one do then after that? After that, Rx, the C end disconnection, we remove the NO2. And what do we do after that? After that, we change this NH2, which is our dummy group, again by functional group interconversion into NO2 so that we can further remove it. Here, NO2 and Rx disconnection, and we get this compound. This is a derivative of salicylic acid, okay? Actually, it was salicylic acid. So, a salicylic acid, the OH group is being protected, are protected. Basically, this leads to salicylic acid. So now, let's see the synthesis. Have we done the correct thing? The salicylic acid is protected. The OH protected, OR, COH. On nitration, what do we get when we nitrate it? See, COH group is meta-directing. So NO2 will be placed meta to the COH group, but since OR group is ortho-para-directing, so NO2 will be placed para to OR. So, you know, the two groups are influencing. Influence of both these groups. We get NO2 para to OR and meta to COH. And this on reduction will give us what? NH2, which is protected by acetylation. It is protected. I had less space, you know, on this wall, so I had to cram these structures. And now what happens after this is again nitration. On nitration, the NO2 group will be directed, because see, NH2 has a stronger influence as compared to the OR. When we are comparing their directive influence, it is the boss, okay? The boss of the reaction. The boss of the directing groups. So the incoming group listens to the boss, okay? So NO2 group is now placed ortho to this NH2. So I think we are getting the correct orientation. Why? See, now what will we do? We will be removing this NH2. Because we don't require this NH2. It was used as a dummy group, This was a dummy candidate, sadly. Iska istemal kiya. Used it and then removed it. Dummy. No longer required. So now this is removed. NH2 group being removed in the presence of these reagents, it is easily removed. After removal, we get NO2, meta 2, OH of course, which has been converted into OR. This is a salicylic acid derivative. And now this on reduction and deprotection will give us the target molecule. So we have the desired compound. As chemists, we are happy that we have followed a certain order. We have not followed our instinct. We have followed the practices well known, the reactions, the mechanisms which are well known in chemistry. Guideline 1, where we saw to it that the orientation, they were disconnected such that the orientations were correct of the synthetic equivalents. Guideline 2, we saw to it that the electronegative groups having a meta-directive influence which slow the reaction are removed first and added last, so that we don't have to use drastic conditions for our synthesis. And moreover, it was also seen that we get the correct orientation. Now, guideline 3, we used another of our chemical reactions that came into force, that is nucleophilic substitution. Earlier it was all electrophilic. In this case, COOH group, how can we get COH group? CH3 is one way, by oxidation of CH3. Here we have used a rather novel method, very simple method. I shouldn't say novel actually, a simple method that the CN group on hydrolysis gives us the COH, and the CN can be introduced by nucleophilic substitution. How? From NH2 by using the rather simple method of Sandmeyer reaction. Guideline 4, where this salicylic acid derivative, these derivatives are used for preparing anesthetics. So the salicylic acid, the OH, has been protected by the R. So in this case, another type of a concept was used. That is because NH2 and OR, they are both orthoparadirecting, but they happen to be placed meta to each other. So how do we use our knowledge of chemistry to place these two orthoparadirecting groups meta to each other? Two unfavorable. How do we fit in two people who are of opposite, who are both sort of, we can say, bosses? How do we restrain? How do we control them so that things go in a very easy way? So yes, NH2 and OR, they are both bosses in their own respects. Okay, both of them are orthoparadirecting. So here we are using another concept, the concept of a dummy group. So that's all for today. So next lecture, I hope you are able to, I'll be giving some assignments. This will be followed up by a few assignments. Let's see. And all the best. Stay healthy, stay positive. Good day.